present a joint work with Carlo Cardinali and Luis Gustavo de Goncalves. So in this exercise, basically, we present an alternative derivation of an objective observation impact. And what we want to do is highlight the interaction between the observation impact and the observation influence in an idealized study. So I provide some remark for the introduction, and then I show the brief derivation, and I explain with analytical and numerical results the interaction between the impact and the influence. So understanding the observation impact and the influence in data simulation is important because it allows us to design better observational network and understand the behavior and correct the behavior of our model. So we have two important metrics in order to quantify the impact of observation on the analysis and on the forecast, and are, for example, among all the diagnostic, the observation influence and the impact that can have several definitions, let's say. So the aim of this exercise is basically derive with an alternative derivation procedure that highlight the interaction between these two diagnostics that are not completely independent. And the idea is to start from an objective functional that measures the error and the result can reduce to a well-known established result by Stomer and Weissman 2016 with some remark on the cost function. And again, yes, the aim is to explore this interaction because it's important, the observation influence that tells something about the sensitivity of the analysis with respect to the observation. But having a huge influence on observation on the analysis doesn't mean that the forecast is getting better. The error of the forecast is improving. So we start with this objective function, as in Cardinali, for example, in which YF4 is the observation at verification time, and HF is the forward operator on state vectors forecasted, so at verification time. Here we are using just one trajectory best, so observation minus this trajectory here. Usually you can use another quadratic term here that is minus the quadratic terms of a trajectory that involve a trajectory that started with an analysis, for example, in which computed with a small set of observation. So the full set of observation actually minus the set of observation you want to study. But it's not important in this case for the purposes of this exercise because the interaction will not change at all. So why we start from this cost function objective? Because if we do not use observation but analysis, we know that analysis and forecast are correlated. Analysis can bring some model bias, and further we do not use energy norm because it's not appropriate for higher level in the troposphere. So we don't want to prove this known issue. We want just to start from proper metric, and then we follow Langland and Bakker 2004 functional derivation. What does it mean? We start with a best linear unbiased estimate for the analysis, and if you use this step, you can use the first variation of the functional and compute it in model space or in observational space. When this delta J or F is positive, it means that there's a degradation in the error. When it's negative, an improvement. So as you can see in this sensitivity gradient with respect to the observation at analysis times, here represented as YAO, here it's hidden implicitly the observation influence matrix. And that, just as a reminder, is defined as the derivative of the pseudo observation at analysis time with respect to the observation, the real observation at analysis time. So if we want to extract explicitly this information here, we need to rewrite a little bit the cost function in order to highlight, to specify better in an explicit way the observation used at the analysis. If we have, if we can use linear operator, short range forecast, and if we consider observation dense, if you want, in a region that can be affected by the analysis observation, then with an ensemble system, we can estimate basically this projection operator, but substitute basically this pseudo observation and verification time, because we can estimate this projection operator with just simply linear regression, as I will show in an example later, because we will have for each observation and verification time, we have an ensemble pseudo observation. We have an ensemble of observation for each observation and analysis time, and so we can create some regression and to estimate this operator. If you want, this is look like as a model operator in observational space that you can understand better if you just for exposition purposes, if you use some pseudo inverse of the H operator, then you can see that this F basically is the model in observation space. But this is helpful just to understand this relation between observation influence and impact, because in this case, if you make explicit the dependence of the analysis observation, when you compute the derivatives of the cost function with respect to this observation, then you explicitly get this influence matrix in the computation. And then you can see how the impact actually is related, not just influence, but other terms are important. So the projection that this F operator that involves all the model, the feedback, how they are represented in the model, the error of observation, and the innovation at verification and analysis time that basically hide the information with respect to our simulation system. So you can have a large influence, but there are all these terms that determine if this large influence actually have an impact on the error, on the forecast error. Now, if you have an ensemble and you estimate this S matrix by using the ensemble, then you reduce the formulation in off space to the computation in off space that it looks like the one derived by Sommer and Weissman in 2016. But there's a difference here because this delta y a o it's representing the whole innovation vector, while in the original formulation and the different formulation of Sommer and Weissman, there's a d prime that comprehend only a subset of observation you are interested in. And this is because we started from a cost function that doesn't contain the difference between two trajectory, basically. But this doesn't have any effect on the purposes of this exercise. So this is just a toy model, for example, in which we want to explicitly show this dependence between all these factors. Again, we can estimate with linear regression this F operator, and since it's linear, this F can be expressed in terms of correlation and in terms of standard deviation that for simplicity are considered proportional analysis and forecast time. And we consider two observations, and the background covariance matrix can be written in terms of this alpha. So we can keep inside information of diagonal terms, and in a similar way, we can consider the observation covariance matrix. So if we use this P and R, we can explicitly then also write the elements of the observation influence matrix. where this R is the ratio between observation error square and background error square. When it's getting larger, the influence reduces. So note that the off-diagonal terms of the influence matrix can change sign. This is important for what I can show you.
You have 3 minutes left.
Yes, putting all these things together, you will have explicitly the expression for the impact in terms of all these elements. If you want, you can also imagine these 16 terms in terms of a sort of Feynman diagrams in which you have the analysis innovation, a dashed line, forecast innovation, connected by this operator, this projection, and with a vertex that is the influence of the observation. And then we can explore what's happened when the off-diagonal terms of the covariance matrices are null, for example. So wider space off. In this case, the impact, it's written in terms of just two graphs. So we have just two terms here. The influence, it's positive, and it's the same for both the observation that looks like independent. And what's happened is that the sign of this impact doesn't depend at all by the influence. And we can also see that it doesn't impact neither the relative impact because we normalized and the influence, since it's the same, go away. And the same can be done with alpha equal almost 1 and beta equals 0, for example. So dense observation with respect to the background scale. In this case, it's also interesting because the two observations actually act as a weight in the impact for one of the observation. But the point is that when you use the relative impact, this common weight go away. So also in this case, for example, the influence, it doesn't matter at the end for the impact, but neither in this case the projection operator. And so here, just as to summarize, only when we have complex cases in which the off-diagonal terms are activated, we have an interplay of all of this quantity that determine the impact. And just to finish, to conclude, there's also a numerical example of Lorentz 63, in which the model in which we observe all the three components. And in this case, the color line represents the influence, the gray line, the impact. And I zoomed in these windows because you have here two different steps with two completely different behavior with respect to the impact of the simulation with respect to the forecast error. In one we have degradation, and one we have improvements. And we can see that also in this case, for example, the S matrix that can be computed is almost the same for the two steps, the same for the projection operator. So what it determines in this case, the sign of the impact, so the sign of the error at the forecast, is the innovation at analysis time. So to conclude, we showed basically an alternative derivation that highlight the interconnection between all this quantity, so influence, innovation, verification, analysis time, projection operator, to determine the sign of the impact. And this highlight the fact that we need to adopt an holistic approach to understand the impact of our system. And there's also a question we need to start investigating using this F operator. So this kind of regression maybe can allow us to determine another way to determine an evolving localization that allow to determine the set of observation that must be used for the forecast, for the verification. Because we can use a connected region with regression coefficient, the correlation higher than a certain threshold. So this is all. Thank you for attention.
Thank you very much, Giovanni. So at the moment, there's one question, yeah, at the UPad, and the question is from Dranan Hu, and is asking, is there any similarity between EnFSOI-Jof and Stiller 2022's approach mentioned in the last presentation? And yeah.
So relation between this method and the one shown before in the previous presentation, you mean?
Yeah, the one developed by Olaf Stiller.
So well, I think that there are several connections. The point is that the cost function here in this case to show this kind of relation uses just one let's say one trajectory for the verification, and not as usual the difference of the two trajectories. So that's why also we find, for example, the formula of Summer and Weisman almost find not exactly the same because we do not use the second part of the cost function, but I mean there's a similarity between all the objective objective impact computation. I would say we simply highlight this interplay between impact and influence and the other elements of the simulation, let's say.
Okay, thanks. There's another quick question by Desuke Hotta. When you introduce the matrix F, do you assume that forecast observation equivalent YF is completely determined by observation equivalent of analysis YA? Does this assumption work when observations are sparse?
Yeah, the point is indeed in the assumption there's the in order to determine the components of this F operator, you need to have a set of observation verification times that can be affected by the analysis observation. And this is also why you should use sort of localization choosing the observation during the computation of observation impact. So, and if they are sparse, it's not really a problem because if the only important thing is that they can be affected by and are correlated with the analysis observation, because the for each observation of verification time, actually you have an ensemble of pseudo observation of the verification time provided by your ensemble, and you have an ensemble of pseudo observation at analysis time. So you always have an ensemble to estimate the components of the forecast, the projection operator F. The point is that the verification observation and analysis observation must contain enough information. They must be affected by each other, let's say.
Okay, thanks a lot.